Okay, I'm going to pick up where I left off here a little bit. In the interest of time, I'm going to minimize the discussion of the Earth and maximize the discussion of Venus and Mars. Suffice it to say, for atmospheric wave coupling, the lower atmosphere is strongly coupled to the upper atmosphere of the Earth. You see this very strongly over 100 to 150 kilometers. Instruments on spacecraft like TIMED, T-I-M-E-D, and others show tides and planetary waves that are very strongly impact the region of the atmosphere of the Earth. What's the situation with Venus and Mars? Again, we're at the infancy of this. This shows a diagram that has wind speeds or phase speeds of waves. So this is positive and negative. Cloud tops is at about this level right here. So this is a 4-day rotation, about 110 meters a second. So any wave launched from this altitude, presumably because of convection, there are convective cells at cloud tops that are quite substantial, hundreds of kilometers in horizontal extent, can launch 4-day waves, presumably at that altitude, 5-day waves from slightly lower altitude, and 9-day waves from lower down still. Whether they arrive in the thermosphere or the upper atmosphere or not depends on the background wind structure. What you see in these different local times is wind structure from the Venus thermospheric general circulation model that my students and I run. And the problem here is to not only launch these waves from regions of the atmosphere where you think they are being created, but also to see that whether they propagate to high altitudes or not. So the 4-day wave has been seen at cloud tops in the cloud data, the photopolarimeter data from Pioneer Venus. They've tracked these wave structures. This is an equatorial wave. They've seen 5-day wave structures. This is a Rossby wave. These are transient waves at equatorial and mid-latitudes, yet they've not been seen in the upper atmosphere data set so far. At the cloud-based level down at this region, 9-day waves have been seen at high altitude, but these kinds of variations, but there's been very little modeling of that done so far. So I put this up there to show you that we're at a very early stage of understanding what's going on in the Venus atmosphere, but it's quite likely that the coupling is very strong. This shows a calculation, altitude and phase. As phase changes with altitude, as it advances this direction, the phase is going down, the energy is propagating vertically. This is the Rossby wave. This is the variation of the zonal wind. Very weak variation, a much stronger variation of the zonal wind for the Kelvin wave. This is a group that runs a GCM simulation in Japan. Now this is the dominant wave that most people think make it to the thermosphere of Venus, and we're all looking for it in data right now. Gravity waves also exist on Venus. This is Pioneer Venus data from many years ago. This shows RMS amplitudes of waves from the CO2 neutral mass spectrometer density measurements. For this suite of orbits, you can see that these RMS amplitudes increase from 130 to 160 kilometers, maybe 30%, 20-30%. So this scale height might be 30 kilometers, and they drop at higher altitudes, suggesting there's some kind of radiative damping or dissipation at higher altitudes. Come on. On to Mars. I was involved in MGS aerobraking, Mars Global Civil aerobraking. So this is a operation where you're trying to circularize the orbit of the spacecraft by using drags or deep dips into the atmosphere. And every time we dip deeply, we're able to sample the atmosphere. It shows different altitude ranges and densities in these units, kilograms per kilometer cubed, as a function of longitude. We began to see density variations fixed in longitude that we did not expect. And if you're aerobraking and you're trying to predict where your next peak or trough is, you need to have some kind of a model that tells you what this structure might be, which means you understand what's creating this structure. So you can see that from 130 to 160 kilometers, you see a longitude structure that remains intact, yet it decreases in amplitudes. So that's one of the early characteristics that we saw. This is another way of looking at similar data, accelerometer data, comparing MGS at the top from Mars Reconnaissance Orbiter at the bottom. Similar season, this is approaching northern summer, aphelion, and northern summer again, dayside and nightside. You can see a wave 2 pattern here that has a 180 degree shift. So this will be a wave 2 and a diurnal kind of wave that has a diurnal frequency. So this is another indication that the waves are really strong in the upper atmosphere. This is at one constant altitude, 130 kilometers. If the density structure of the atmosphere is enhanced, it has peaks and troughs as a function of longitude, and if the peak of ionization occurs at tau equals 1, optical depth unity, then you might expect the ionization height, peak height, to move up and down in altitude. And that's what was seen. Let's see, the observations are solid curves right here with 1 sigma error bars, and the calculations that I made are the triangles, wave 3 pattern, wave 1, 2, and 3. So indeed, there is a correspondence. This was discovered early on, and it's a clear indication that we have a photochemical ionosphere at these altitudes, and the atmosphere is responding exactly as you would expect. Gravity waves at Mars certainly exist. This is probably not the best picture. The topography on Mars is just gigantic. And launching waves, these would be stationary waves, and waves could be launched at middle altitudes that are not connected to topography at all. This shows evidence of some waves in the high northern latitudes during northern winter. This is from Odyssey. The scales, the horizontal scales, are up to a few hundred kilometers. Typical delta rho over rho amplitudes are 5 to 50% in this altitude range, and they seem to maximize over this longitude range. No one knows just why yet, but it's clear that gravity waves are getting up to higher altitudes on Mars, and they're launching from below 100 kilometers. Okay, one aspect that doesn't translate from planet to planet is the Mars dust storms. The dust oscillates from season to season. This is a latitude versus time plot. This is perihelion, so this is summer in the south, summer in the north, summer in the south, summer in the north. So you can see there's a pattern. This is integrated optical depth in the vertical, and I'll not describe the units right here, just suffice it to say this is the scale from near 0 to 0.5. You can see that there's a repeatable pattern of perihelion periods when the opacity is quite a bit larger. The dust loads in the atmosphere are quite a bit stronger. And sometimes, some periods are quite a bit dustier than others. And this is a current state-of-the-art, right at the edge of a research project, trying to understand exactly what launches dust that differs from one Mars season to the next. What happens is the dust warms the lower atmosphere, expands the lower atmosphere, and the upper atmosphere rises because of that expansion. So the ionospheric peak will rise, and the upper atmosphere responds to this. So this is a plot of density at a constant altitude as a function of MGS orbit number. These are model calculations I made ahead of time for standard conditions, no dust storms. And this is what happened in the northern latitudes as a function of time. Orbit 49, 48, 49, a factor of 3 jump, and a decay of that density at that constant altitude and location over time. This occurred during Thanksgiving, and our entire team was taking it easy, and we were all called back to work very, very quickly. They had to pop the spacecraft out of the orbit, raise its periapsis altitude 10, 15, 20 kilometers to get out of danger. And they rode it back down over time. So this shows a variation. This is a couple-month period here as the orbit numbers increase to the right. So this is a very strong response. Remember that you may or may not remember the dust storms are launched in the southern hemisphere. So this is a northern hemisphere effect at 130 kilometers, and you see a response in just a couple of days. So the overturning circulation is enhanced, and you see that effect at northern latitudes very, very quickly. Some work was done with the accelerometer data to try to unfold what the zonal winds might be. So this is a nearly polar orbiting spacecraft So zonal winds would be cross-track, and if you take account for all the moment forces on the spacecraft, in a lot of work, you can unfold what the cross-track winds would be. So this is wind velocity in meters per second, and this shows the data in the blue and the error bars that go with that. This is before the storm, storm onset, and storm decay. I think the other plot ended 200 orbit 200 here as well. So this is a factor of 2 increase in zonal winds in just a few days. This is an extreme event. These were model predictions, assuming no dust storm. Dust storm, as I mentioned, as you inflate the lower atmosphere, the upper atmosphere will respond. This is the height of the F1 or photochemical peak as a function of solar zenith angle. As you move into a slant path, the point at which you encounter tau equals 1 will rise in the atmosphere. And that's exactly what you see for this curve here for a model simulation of the data points indicated here from various radial occultation measurements. However, during the global dust storm of 1971, when when Mariner 9 first arrived, the entire planet was shrouded with dust. And they basically waited for several months to do most of the experiments, except for the radio occultation. And they showed the ionospheric peak had been raised nearly 20 or 30 kilometers. And this shows a recent plot that Paul Withers made. This is altitude as a function of orbit numbers. So this is a decay over a period of about 30 days in this 80 orbit duration. And it dropped about 10 kilometers over 30 days, and it still hadn't come down to the original level again. So the bottom line here is this is the one coupling with the lower atmosphere that Mars has that's unique, other planets do not possess. There's not been evidence that connects the two of those as yet. However, it should be. It just hasn't been observed. The instrumentation hasn't been there to do that. Presumably, as you're piling dust into the atmosphere, the convection cells will be launched and the gravity waves with it. But there's been no measurements at the same time. It's a good point. Okay, I'm going to switch gears here with the remaining time that I have and show you some numerical experiments that we've run in which we've dialed down the geomagnetic activity for the Earth and put it on a rather equal footing with Venus and Mars that are primarily solar driven. I wanted to find out what the heat balances were and what the response of the atmosphere would be like, and see if we could reproduce the solar cycle variations for Venus and Mars on the Dayside, and what solar forcing alone for the Earth, what that variation would be, and what the heat balances would be. We have a collection of Mars models from thermospheric GCMs from here at NCAR. I was once a postdoc here and developed the Venus model. The TIE-GCM has been in operation here at Mars, Ray Robles' model for many, many years, and a Mars model as well. The story that I always like to tell here is when I was a graduate student, Ray Robles came to visit at Michigan, and he pulled my thesis advisor, Annie Nagy, aside and said, "I have something very interesting to show you." He had forgotten to turn on the rotation of his Earth model. And it looked very Venus-like at solar minimum conditions. So I got a PhD thesis out of that simple mistake. I spent 4 more years developing a very detailed model, but the guts of the fundamental parameter change was right there. And later, Ray had the insight this time to turn off the magnetic field at Earth, and he got a very Mars-like situation. So these models are very useful for intercomparisons, and we often learn things as we do so. The altitude range of the different models is listed here from near cloud tops to the top of the thermosphere for Venus. This range for the TIE-GCM up to near the exobase, and for the Mars from the middle atmosphere up to the exobase as well. Similar vertical resolution, about a half or a quarter of a scale height. Vertical horizontal resolution is indicated here. Neutral species, this is as indicated for CO2 planets and for the Earth, temperature and 3-component winds, the photochemical ions for the 3, and for O+ for the Earth. This is a diffusion at the highest altitudes. The minor neutrals and radiative cooling. CO2 cooling for Venus and Mars are important, and this combination for Earth. I mentioned earlier that CO2 cooling is extremely important for Venus, and we'll just see how important here in a minute. There's the time steps for each of these models. So for Venus, the unique processes for the planet are the very strong 50-micron cooling, wave drag that we use to simulate upward propagating gravity waves that we don't know very much about right now, and a component of the cloud top retrograde super-rotating zonal winds that we put in the model and prescribe to get an asymmetry in the circulation, a very small asymmetry, but one that's observed. This shows plots as a function of local time and latitude. The top panel is solar minimum conditions. The bottom panel is solar maximum conditions. This represents a condition that might be similar to Venus Express, which is observations that have been made since 2006. And this is the Pioneer Venus time period. So you see superimposed temperatures in the colors, and the arrows indicate the magnitude and direction of the neutral horizontal winds. In both of these cases, you see divergence of the winds near noon and convergence on the night side. The winds are the stronger across the terminators, and they're stronger across the evening terminator, where the subsolar anti-solar flow and the retrograde zonal flow add, and the reverse across the morning terminator. Temperature variation here is similar to what's observed, about 80 degrees Kelvin, and similar to this ratio variation that I mentioned earlier. This shows that this temperature variation with solar cycle really takes place on the day side above about 135 kilometers, and this is where the EUV heating is most important. So that makes perfect sense. Very little variation on the night side, just as observed. Come on. Back. This shows the heat balances for solar minimum and solar maximum conditions at noon, local noon. So I'll guide you through altitude and temperatures, degrees Kelvin per day. The scales here are a little bit different. I apologize. Solar minimum, this is EUV heating. This is near-infrared heating, 1 to 3 micron bands, which is important at Venus. 15 micron cooling. And these terms with the spaghetti in the middle, adiabatic cooling and total advection, these are the dynamical terms. And molecular thermal conduction, which works if there's a vertical gradient in temperatures. So you can see the major balance between the radiative terms, heating terms, is with the CO2 50 micron cooling. For solar maximum, now you'll see that the solar EUV heating dominates, has a peak that's much larger than the near-infrared heating. It really doesn't change much with magnitude, which you would expect. CO2 50 micron cooling is still the dominant cooling agent. So for Venus, we believe that this is the reason that the solar cycle variation is rather modest or weak, and also the temperatures are cold, even though it's the planet that's the closest of the 3 to the sun. This is electron temperature variation, solar min to max, just for completeness. You do this now for Mars. We now put in this variation of the orbital eccentricity, a similar 15 micron cooling scheme. We couple it now with a lower atmosphere model that allows us to propagate up gravity waves, tides and planetary waves. It shows the same kinds of plots again, latitude, longitude, and noon is at the center, and this is the midnight at the edges. This is the evening terminator and the morning terminator. You can see a cold day side, solar minimum conditions, solar maximum conditions. The variation of temperatures here is about 110 Kelvin at local noon. You can see that this ring of hot temperatures at high latitudes and near the terminators. What's happening here is that winds are upwelling on the day side and sinking at the poles, and the downwelling provides adiabatic heating. And this is thought to be a very strong mechanism for heating at the high latitudes on Mars. Very little of this has been observed yet, so we hope to have data that would allow us to address that. Winds are divergent from the day side and convergent on the night side. You see cold regions near the equator. It shows the temperature variation at local noon again above about 120 kilometers, where EUV heating is important. This is where the temperatures change dramatically with the solar cycle. If you include the variation of the seasons, that variation of temperatures increases significantly. Come on. This is the heat balance at local noon. This is the combined near-infrared and EUV heating, and this color right here. This is molecular thermal conduction, 15 micron cooling, which is rather weak at Mars, and then the dynamical terms. So again, this is consistent with the plot that I showed you earlier. There's upwelling on the day side that's quite strong, providing cooling, subsidence at the terminators, and the poles that's providing heating. This polar warming has been observed in certain time periods at the solstices at Mars at about 120, 130 kilometers warmer temperatures than would be expected. It's very limited measurement, and so we're looking forward to seeing further information about that. This shows that electron density peaks, stays at the same altitude, obviously. There's no underlying change in the underlying atmosphere, solar min to max variations close to what's been observed. Now for Earth, we use this ion neutral chemistry from Ray Roble, include the 15 micron cooling, the nitric oxide cooling at 5.3 microns, high altitude, 63 micron cooling for oxygen, and we keep the KP very low to ensure that we have mostly solar influence. Again, this shows latitude and local time, noon at the center, evening and morning terminator. So you see winds that are divergent from the mid-afternoon and strong across the terminators and onto the night side. The peak in temperatures is in the mid-afternoon, similar to Mars. So the rotation rates are very similar, so the Coriolis terms impact the transport and allow this to be so. So that's comforting that that's happening, similar between the two planets. This temperature variation now is a little over 600 degrees Kelvin, and the horizontal winds are varying appropriately. Again, this is for very low solar geomagnetic activity. Variations in temperature due to solar EUV-driven heating is manifest above about 125 kilometers. Heat balances now. Let's see, this is solar minimum and maximum, so let me just talk about solar minimum first. Solar heating is this red curve. The yellow is the total, so that's almost identical. The heat balance, the cooling terms are the nitric oxide cooling right here and the CO2 cooling. CO2 cooling is important only at the bottom, nitric oxide at higher altitudes. That nitric oxide increases significantly at solar maximum, and it does so also during geomagnetic activity. So it's the thermostat on Earth that Mars does not possess. And the Dayside electron temperature variation for just simulation at one location, local noon. So I just want to stop there and summarize and say that for these model simulations, we run tests to try to compare the heat balances in the three planets. And the CO2 cooling plays a far different role on Venus and Mars than it does on the Earth. And these other two planets have no counterpart to nitric oxide cooling, which is the thermostat that is more important than the Earth's upper atmosphere. Looks like you got a question brewing there.
What is the conduction cooling in Venus and Mars? Is the transport of hot electrons out?
This is neutral thermal conduction. So as you have a vertical temperature gradient, you tend to move down gradient and cool the atmosphere. It's trying to re-equilibrate with the conduction coefficient to drive that. So basically what it does is it takes heating that's deposited at higher altitude, conducts it down gradient where it has an ability to be re-radiated at the bottom with CO2, 15 micron emission. So it's the same kind of process on the three planets, but where that cooling is placed makes all the difference. What altitude it's placed at makes all the difference. And for Venus, it's placed at exactly the right altitude to balance the heating that's available. Did I answer your question? I did. I didn't talk about it. Sorry. It's this one. It's labeled strangely. It's this curve right here. So it does exist, but it's not, for solar maximum conditions, it's not the primary cooling agent. For solar minimum, it's more important. Good point. Keeping me honest. Okay, I'm coming into the home stretch here. Solar flares, I mentioned that they've been observed at both Mars and the Earth, and we've done some calculations for both to try to see their relative effects. So this shows solar flux and wavelength in angstroms. This is from one of the books before. This is the Halloween storm again. Pre-flare is the solid curve, and the flare is in the lighter colors. Variation at the solar soft X-ray range is quite significant, but it's not zero in the EUV, so the full spectrum is actually important to use in our modeling effort. This shows the CHAMP data that I mentioned to you before in a global ionosphere thermosphere model from Michigan that's been used to model that variation. This is the observed variation. This is the model variation. This is about a 15-20% variation at 400 kilometers or so. So it's shy of what's observed, but in the right direction. This is the TIE-GCM model responses of the same storm. This the time the storm onset is in this location right here. This is temperatures, mass densities, electron densities, and nitric oxide densities at these different altitudes. And each of these responses has different time scales for their decay, which is important to get right, and it's likely very dependent on the thermal balances in the atmosphere and the ion chemistry that you have included. This is an enhancement of electron densities in the E region due to this Halloween storm once again, or flare. This is a variation that you can see pre-storm and storm level. This is rather significant at the lowest altitudes, almost a factor of 10, but not so much at higher altitudes. Again, that's consistent with the solar X-rays, the hard, soft and hard X-rays being most important down here where they deposit where the ionization takes place. Let me skip this because I'm running short on time. Let's go back to April 15th once again. This solar flare this is GOES measurements from this April 15th time period. So the onset of the flare is right here. This shows the data that I presented earlier for Mars. This shows the Mars calculation from a global ionosphere thermosphere model from Michigan as a function of time. And this is the peak and its decay. And this is the variation in the Earth global ionosphere model for the same date and the variation in the ionosphere. Our prediction is that the response on the Mars ionosphere is quite a bit larger than that for the Earth. Yet our data is quite limited. So let me summarize with some takeaways here. I'll go through top side, bottom side, coupling, and then a few thoughts for the future here. I've spent a lot of time going through the different heat budgets on the 3 planets and their responses to solar cycle variations and the EUV fluxes. Venus has the smallest variation and the coldest temperatures, yet it's the closest to the sun. The CO2 cooling is likely quite important. This may not sound like a big deal to you, but we've been working on this problem for 30 years. And finally, the atomic physics measurements were made for CO2 collisions with atomic oxygen and other species that we could actually model it correctly. It took 30 years for that to come about. Very strong thermostatic effect for Venus. Mars has large-scale dynamics and thermal conduction that seem to hold sway over CO2 cooling and provide a solar cycle variation of temperatures that's midway between Venus and the Earth. The Earth is regulated by this nitric oxide cooling, and as Mark pointed out, thermal conduction at the highest altitudes as well. So the thermostats are somewhat weaker than either of these 2 planets, and it has the largest variation in temperatures over the solar cycle. So the bottom line here is CO2 cooling is profoundly different we believe, in the thermal budgets of the 3 planets. And it's also important in space weather effects, solar flares as an example, because that same kind of thermal balance structure will also impact the kind of response you get from solar flares. Topside coupling also, I didn't mention it, but we're just beginning to model and understand what might be happening with the O+ heating from precipitating ions on the upper atmosphere. The temperatures variations could be significant. It's certainly something we want to look at very carefully with MAVEN and watch storm events and see exactly the response of the atmosphere. It would be great to have an alignment of Mars and the Earth so you could watch an event take place and see the same side of the sun at Earth and at Mars and watch the response of the upper atmosphere. This is a chance opportunity. We'll look for them, but that would be the best that we could hope for. All 3 terrestrial planets have upper atmospheres that are significantly altered by propagating waves and tides. I didn't give it due justice for the Earth, obviously, but we've learned a lot from air braking at Mars, and what we're learning from Venus is in its infancy. But what we have seen so far is that there cannot be an upper atmosphere that isn't responsive to the lower atmosphere on any of these 3 planets. The sources for the waves are quite different, though. Variable dust heating and topography for the Earth. Okay, that has no counterpart. Dust heating has no counterpart on Earth and Mars. Lower atmospheric dynamics and thunderstorms are important for launching waves that actually make it to these high altitudes. That has no counterpart. Thunderstorms on the other 2 planets. Venus has very strong cloud top convection that the other 2 planets do not have. So each, in its own way, is launching waves and providing us a laboratory to look at the upper atmospheres. Dust storms, this is profoundly interesting to me personally because it really is the measure of how good your model responds to this forcing is an indication of whether you've included the processes correctly, the heating and cooling terms, and the dynamical terms. Are we missing things? We will find out as we try to reproduce an evolution of a dust storm. It's not been done yet successfully. Finally, I'll come into the finish line here. MAVEN is launching this November. We'll be looking at solar wind inputs, solar energetic particles, solar EUV inputs in 3 solar diodes, as I mentioned here. We're going to look at the solar forcing, the response of the solar wind ions and electrons. There'll be a neutral mass spectrometer, an ion mass spectrometer for thermosphere ionosphere structure. So the goal here will be to piece together the reservoir, the thermosphere ionosphere reservoir for ions and neutrals that escape, characterize the exosphere, and characterize the solar wind, and piece these together and begin to understand in the current day how escape is taking place. Hot oxygen escape, ion escape, and other escape mechanisms. Characterize those carefully for present day. The goal then would be to look at G-type stars that are similar to the Earth and their history, estimate what the solar fluxes might have been in the past, and run these models backward in time. And it's you do an integrated measure of the loss of oxygen and hydrogen over time. You may have some estimate of how much water will have been lost from Mars over the age of Mars itself. The caveat to that is what Sabina and I were talking about during the break, is that it's possible that heavy bombardment is the wild card here, and when the crustal magnet, when the intrinsic magnetic field turned off, because that will also throttle the loss processes as well. So stay tuned about Mars. And U.S. has no plans to go back to Venus anytime soon, but Venus Express is a highly successful mission that is in the middle of characterizing these wave responses in the upper atmosphere. And it's been a very exciting mission. So, questions? they're beginning to talk about these at Berkeley and develop. I mean, with these crustal fields having the structure that they do, there's likely to be these currents that are running in that region of the atmosphere, and they're beginning to put together models to do just that. They're not very far along in their analysis, but this is something they're quite concerned about, particularly on the night side of Venus, night side of Mars. The ionosphere there is very spotty, patchy, and this may be one of the reasons why. It's just not been taken into account. So that's something that will be looked for in the data, and these models hopefully will address that. It's the counterpart to the dynamo at Mars, and people have started to think about it. Good point. Are you tired, friend?
No, I had a question.
I saw you holding your head going, whoa.
It just got, I think it was stripped away by the flying magnetic field.
Well, friends, can you have a question? Anybody know homework? I know you just want to.
By the way, we did pass out 2 sets, one for Marina's talk and one for mine, so you should all have a stapled batch and a single page from me.